We've talked about gaining and losing electrons, so let's look a little bit about ion formation. So, the forming of ions. We'll recall some terminology here. Cations are positive ions which result from the loss of electrons. So, when you lose negative charge, you're going to have more positive than negative, and that's going to result in a positively charged ion. Anions are negatively charged ions, and they result from the gaining of electrons. So gaining negative charges makes you negative. Here's a little look at the periodic table. There is our line which separates our metals from our non-metals. All metals, everything to the left of the stair-step line, loses electrons and forms cations. That's part of the identity of metals, is that they're cation forming. Whereas most of our non-metals here to the right of the stair-step line are going to gain electrons and become negatively charged. Okay, so let's go back to our Offby diagrams of period 3 elements. So here we have magnesium. Magnesium has 2 valence electrons. The goal, of course, here is to get to 8 valence electrons, or an octet. So we have a couple of options. First, magnesium could gain 6 electrons, which would get it to 8. That would be one option. A second option would be to get rid of 2 electrons, which would reduce it to 8 valence electrons, because it would no longer have electrons in the third energy level. And so electron configuration for magnesium, when it loses 2 electrons, be 1s2, 2s2, 2p6, and that would take it to 8 valence electrons. It's no longer a magnesium atom with 12 electrons. It is now magnesium ion, Mg2+, with 10 total electrons, 8 valence electrons. So that's typically how a metal is going to go about getting to that octet. Okay, let's look at something to the right of the stair-step line. So let's take a look at sulfur. Sulfur has 16 total electrons, 6 valence electrons. Again, you think about ways it could get to 8 valence electrons. Well, it could get rid of all of its third energy level electrons, which would leave it 8 electrons in the second energy level. An alternative would be to gain 2 electrons. Again, these things are going to go through path of least resistance. When you gain an electron, it is always going to be harder to gain the next electron, because your effective nuclear charge is going to be decreased every time an electron is added. When you take away an electron, it is going to be always harder to take away the next electron, because the nucleus can then hold the remaining electrons tighter. So path of least resistance here. It's way more likely to gain 2 than it is to lose 6. And of course, if it gains 2, then we're going to have 6 electrons in that 3p. That's going to be 8 valence electrons. It's no longer going to be a sulfur atom with 16 electrons. It's going to be an S2- ion with 18 electrons, and we refer to that as a sulfide ion. So again, everything to the left of the stair-step line is going to lose electrons and become positive. Non-metals in general to the right of the stair-step line are going to gain electrons and become negative. So let's talk about naming ions. If we're talking about what are called monatomic cations, that means one element loses electrons and becomes positive. This is in contrast to what we will later learn are called polyatomic ions, which are compounds that gain or lose electrons, more than one element, or more than one atom anyway. So monatomic cations, when they lose electrons and become positive, they retain their name, but you add the word ion to the end. So for instance, aluminum, if it is neutral, would be referred to as an aluminum atom, but aluminum loses 3 electrons to get to that noble gas electron configuration and becomes Al3+, or the aluminum ion. For monatomic anions, we change the ending of the element to IDE. And so chlorine, Cl, would be the neutral atom. And if it gains an electron and becomes Cl-, needs only 1 electron to get to that noble gas electron configuration, we would refer to it as chloride. You can also refer to it as the chloride ion. But you don't need the term ion for monatomic anions because the I tells you it's charged. For monatomic cations, you absolutely need the word ion at the end of the element name. Otherwise, you don't know the difference between the atom and the ion. Let's talk about dot structures for ions. So first, look at each of these elements, and what you might want to set up on your paper somewhere is ignoring the charges. If we were just talking about the beryllium atom, what would a dot structure look like if we were just talking about an atom of arsenic? So you might write these 4 elements down just as a quick practice. Without the charge, what would their dot structures have to be? Go ahead and pause the video and do that. Okay, if you got that done, here's what the answers ought to look like. So 2 valence electrons in beryllium, so we get our 2 dots there. Arsenic has 2 paired electrons and 3 unpaired electrons. Fluorine with 7 only needs to gain that 1 electron, and potassium with 1. For cations, when we form the ion, beryllium's going to lose those 2 electrons to get to a noble gas. That's path of least resistance. So we're going to put beryllium in brackets and put that charge on the outside. If you're just writing the ion for beryllium, you can just write Be2+. The brackets are just a convention when you're talking about doing electron dot structures. If we're forming cations, typically we drop all the electrons off, even though that beryllium has 8 valence electrons. Because it's a cation, we typically don't show them. You just have to infer those 8 valence electrons from the charge on the ion. For anions, we go a little different way. We go ahead and add all of those valence electrons to get to 8 because they're gaining and not losing, and then put them in brackets and put the charge on the outside. So that would be an arsenic or an arsenide ion. Again, anions we changed to IDE. And then the beryllium would be a beryllium ion. So, given that, can you draw a dot structure for the fluoride ion? What happens when fluorine gains 1 electron? Why don't you take a second, pause the video, and jot that dot structure down. And if you did that, you should have gotten this situation right here. So, fluorine's going to have 8 valence electrons. We're going to put that 1 minus charge on the outside. Again, if it's a 1, you don't need the number. You can just put minus. But 1 minus or minus either way is fine there. Going down to this last one, we have potassium. Again, maybe you take a second, pause the video, draw the dot structure for the potassium ion. Again, for cations, we're going to take all the dots away. We're going to put it in brackets, put the charge on the outside. So it's just a convention for drawing dot structures. For cations, we're going to drop all the electrons, put the charge on the outside of the brackets. For the anions, we're going to add those 8 valence electrons, put the charge on the outside of the brackets.